Dear students, welcome to Architecture and Programming Models for GPUs and Coprocessors. We're still talking about rendering algorithms, and we're going to finish off this topic today. In the last session, we started talking about parallel rendering algorithms, and we learned about Molnar's taxonomy, who basically formulated parallel rendering as a sorting problem, and we learned about the sort first, sort middle, and sort last algorithms, where sort first basically was a screen space subdivision. Sort middle was an algorithm that distributed edge equations among raster engines, and where sort last is an algorithm that subdivides the geometry and distributes it to the rendering processors, and in the end sorts the intermediate images that result from rendering those partial geometries into visibility order. And in this session, we're going to concentrate on the sort last parallel rendering algorithms because of its high relevance to the scientific visualization community when it comes to rendering large datasets. So an issue with the sort last compositing algorithm is that at scale, that is, when we add more processors to the problem, then we'll usually observe that not rendering but compositing will become the bottleneck. That is, the process of taking those intermediate images and compositing them to a fully rendered image that includes all the contributions from all the processors. And this is due to the fact that whenever we subdivide the rendering problem more, then we distribute less geometry to the individual processors. So the workload on the individual processors will be lower, and at the same time, the region of image space that the individual processors are responsible for will become smaller. And therefore, quite often, sort last parallel rendering isn't limited by the rendering algorithm, but is more often limited by bandwidth limitations and network contention. And in particular, if we implement this naively, like if we use a naive algorithm to distribute the intermediate images over the network, then we will usually observe contention and heavy load on single nodes, for example, on the node that performs display. Like in a very naive approach, we would just have each processor render its share of the image and then send its complete share of the image to the display node. And that would more or less serialize the network communication to the display node, and that's of course bad, because that, for a handful of processors that might work, but that doesn't scale very well when you're rendering on 64 or even more processors. Then this just would not scale. And for those reasons, we'll now discuss smarter alternatives to the naive compositing approach. And the very first algorithm that we will discuss is the so-called direct send algorithm. And I'll first provide a bit of an intuition how the direct send algorithm works. And the direct send algorithm is actually a building block. So the compositing algorithms that we will discuss after, some of them will actually be based on the direct send algorithm. So an important intuition that we should have about the direct send algorithm is how work items are assigned to processors. Like direct send really only refers to the communication pattern that we perform in the end when the whole rendering algorithm already ran through. That is, the direct send compositing algorithm is independent of the actual rendering algorithm that we use. And therefore, for our discussion, we have to consider two different processor assignments. We, on the one hand, have something that I will call the rendering assignment. Like when we're rendering, each compute node is responsible for its share of the data set. So each processor will render a part of the geometry. And for simplicity's sake, we'll in the following assume that each processor renders a full screen image. Like earlier, we saw that when the processor is only responsible for part of the geometry, then you usually don't have images that have the size of the whole window or of the whole screen, but usually only of a part of it. And we'll now, for simplicity, assume that the intermediate image that the processor creates will just have the size of the whole screen. like there are certain situations where this might happen, like depending on how you on your viewing direction, on the camera's position and orientation, this might happen. But in general, it doesn't have to happen. We just assume that each renderer produces full screen intermediate images. So we have processors P1, P2, P3, and P4 rendering in parallel and creating 4 intermediate images. And this assignment of geometry and therefore of intermediate images to processors is what I will call the rendering assignment. And like you can see that there is an order to those images here, but the processors aren't aware of the order of the image. They're only aware of their share of the geometry. Like they render their geometry and then they'll create images, but they're not aware of the other processors while doing so. So this will give me those 4 intermediate images. And now it is important to note that in the following, the processor to work item assignment that we will talk about is a different one. The work items that we process now will be assigned to processors in a different way than we assign the rendering work items to processors, and this is important to note. Like there is this rendering portion of the algorithm, and we now have each processor holding its share of the intermediate images, but we'll now have a different assignment of work to processors in order to composite the image. Like the assignment is still there in that each processor holds its own intermediate image, but we'll now assign responsibilities differently. We'll now have an assignment where each processor is responsible for a part of the screen. Like here, I've just subdivided the screen into blocks, and this is actually not a necessary assignment. Like it could be different, but we have some assignment of screen space to processors, and the assignment in general is a different assignment than the one that we used for rendering, like the assignment where we assigned geometry to processors. So we on the one hand have a rendering assignment where each processor is responsible for its own share of the geometry and renders its own intermediate image. And on the other hand, we have an assignment where each processor is responsible for its own share of the screen space and of the final image that is going to be rendered. So this gives us some new assignments, some new processor assignment. And in this setting, like we still have this rendering assignment in a sense that each processor still holds its own intermediate image. And for those reasons, we'll now have to send data, like we'll have to send intermediate images. But in contrast to like a naive approach, not each processor will not send like its whole image to one processor, but each processor is like responsible, like holds its whole intermediate image, and it will only send a part of the image, like this upper right quadrant here of the image, to the processor that is responsible for compositing this part of the image, right? So each of the processor from the rendering assignment holds its own intermediate image, and we'll now have an assignment where each processor is responsible for a part of the image, and each processor will now send its share to the processor that is responsible for compositing this part of the image. And now we're only talking this upper right quadrant here of the image. Again, now each processor will only send its upper right quadrant of the image to processor P4. And we will do this for all the other parts of the image too, like in this example for all the other quadrants of the image, we will do this too. And this can like obviously happen in parallel to some sort, and this is what we will call direct send. So this will be what we will call the direct send algorithm. And here's the same setup again, where you can see that we have a different assignment of geometry to processors and of image regions to processors. Like each processor handles its own share of the geometry, will produce its own intermediate image, and then will send parts of the intermediate image to the processor that is responsible for compositing this intermediate image. So that means that we're like having each processor being responsible for 1 over p parts of the image, and all processors send p minus 1 times that to all the other p minus 1 processors, because this is just the remaining part of the intermediate image that needs to be sent over the network to the other processors for compositing. So, and then in the end, what we have is like a shared result, like a distributed result, right? Like each processor, P0 through P3, holds a part of the image, and that part is fully composited. So the question is now really what we do with this, and like in general, one would have like the display node gather those composited images to form a full image, like a full size image. This approach is actually pretty flexible. Like when we're, for instance, rendering on a tiled display, like where we have a setup with multiple monitors, and each monitor is assigned a certain region of the overall image, then we're maybe even good with a shared result. And on the other hand, the real bottlenecks occur not from sending fully composited images, like the display node in the end gathering the partial images. This is not really a problem. But what's really a problem, and what leads to bottlenecks, is the communication up front that is concerned with sending intermediate images. Like you can think of those intermediate images as fragments. They're basically like fragments because they are not fully composited yet. Like they are partially composited, but in regards to the fully composited image, they are still fragments. And this part of the algorithm where we send like fragments around is the really costly part. And then in the end, if we have a composited result, it doesn't really matter so much if this composited result is present on a single processor, or if it is a shared result and potentially needs to be gathered by the display processor. So and here is the direct send communication pattern. Like the arrows in this illustration indicate who sends data to whom. And it's important to note that this is not a screen space subdivision into 16 tiles, so the image shouldn't be mistaken for that. But it is rather a think of it as a screen space subdivision into 4 different regions of the image. Like the saturated green, red, yellow, and blue indicate the portion of the image, and they also indicate which processor is responsible for this portion. Like processor P0 in this case is responsible for compositing 1/4 of the image, and the processors P1, P2, P3 will send their intermediate images to P0, but only the portion that P0 is responsible for. And the same is true for P1. Like all the other processors send just the portion that P1 is responsible for to P1. And the same is true for the other 2 processors too. And we can see from that there are there are lots of concurrent messages that are being sent. So in comparison to the naive algorithm, we already improved things a lot. By that, we're not sending full images anymore, but we're only sending image portions. So we have clearly distributed responsibilities, which processor is responsible for which portion of the image, and then the processors only send certain portions around, and then in the end we have a shared result. So the overall load with that, like the number of fragments that is being sent around with that is being minimized now. But the communication pattern potentially isn't ideal, like when we add many more processors to the equation. And for those reasons, people often use alternatives to direct send, and those alternatives are round-based. And in this regard, direct send can be thought of as a one-round algorithm. Like we have one round of communication, and then the whole image is distributed over the network. Like all the intermediate images are distributed over the network in a single round. And in order to mitigate the effects from lots of concurrent messages, people divide this type of algorithm into rounds. And that brings us to a discussion of so-called tree-based and round-based compositing algorithms, where direct send is like a special case where the tree that we're operating on has height 1. And like in general, we'll have a tree of rounds where each round represents a level of the tree. And the focus now is just on finding a good balance between the number of concurrent messages that are sent and the bandwidth requirements that are necessary for a single message. So, and when we discuss a round-based algorithm, we'll start with a very naive approach just to illustrate which problems this naive approach has. Like, the naive approach would just go as follows. Like, we would in each round, we would have a processor send an intermediate image to its direct neighbor. And then only the direct neighbor will perform compositing, and then in the next round, one of the two neighbors is just completely inactive, they will not do anything at all. And then finally, we'll have a fully composited image, and that image will be available on a single processor. The communication pattern of this can be very much thought of as the same communication pattern that we discussed for reduction. Like when we discussed the algorithm parallel reduce in the parallel algorithms section, the communication pattern was very similar. And we had this very same problem with reduce, where after each iteration of the inner for loop, we had an inner for loop that would perform iterations, and each of those iterations again was like a parallel for loop, and after each iteration we would cut the number of processors that are participating in the computation. We would cut them in half, right? So that in the end only one processor would perform the addition or whatever binary operation we use for a reduction, so that when we go up the tree, fewer and fewer processors actually participate in the computation. That is, of course, problematic because it can lead to starvation. The basic idea is just that we start, for instance, with 8 processors, and those 8 processors were rendering and now have rendered intermediate images. So we have 8 intermediate images, and from the fact that we have 8 processors, we also know the height of the tree and therefore the number of rounds. The height would just be proportional to the logarithm of the number of processors. In our case, would be 3. And in the first round, we'd have each processor, each even processor, send its whole intermediate image to the odd processor, right? We have processor 2 sending to processor 1. 4 sending to processor 3, and so forth. And the odd processor would perform compositing. So in the next round, only the odd processor from round 1 would participate. So we would have 4 processors on those rounds, and the formerly even processors would now idle. And then we would do the very same thing again, right? We would now use the formerly odd processors, and those would form new pairs. And they would again send each other, the now even processor would send its full intermediate image, which now includes the results from the 2 processors that were active on the round before, would include this whole intermediate result, and the odd processor would again composite that image. And then in the final round, we would only have 2 processors that participate. What we now have. We now have a pattern where we send whole intermediate images. This is actually not so bad because we're sending those only in pairs. We only have pairs of processors that send each other intermediate images, and we don't have that problem with contention, where a bunch of processors send their image to one processor. So that's not really so bad. But we now also have distributed the number of concurrent messages. So we have fewer concurrent messages now because we subdivided this into rounds, and that means we only have so many concurrent messages per each round, and the number of concurrent messages actually halves per round. But the problem is really that the portion of the image is always the same. All the time, we have on each round, each processor compositing a full image in regards to the screen size. And therefore, on the current round, only half the number of processors can participate compared to the round before. And that's, of course, problematic. And there's a very simple trick that people use to mitigate that. And the trick is based on the fact that the work that is done on each round has some type of granularity. When we have a full image, we could imagine that maybe on the next round we maybe don't have each processor composite a full image, but maybe only a half of the image. And that means in general we have enough work so that each processor could perform some work. Like in the case of the reduction earlier, like when we were really performing a binary operation like a sum, then there is just really only so much work to do. But in our case, like we we're operating on full images, and like it's conceivable that one would instead cut on one of those levels the images in half, and then have more processors participate than we would have with this simple naive approach. And this is basically the idea behind the binary swap algorithm that we will discuss next, which is also a tree-based algorithm and a round-based algorithm, but is less naive than this simple approach that I'm presenting here. So we will now discuss the binary swap algorithm, which solves this problem that when we move further up the tree, that more processes become idle and don't contribute in the actual work. And the binary swap algorithm is also a binary tree-based algorithm, but it works a bit differently. It works by, like, on each round having pairs of processors being responsible for a common image region. And then after the round, the two processors basically swap responsibility. And then another important aspect of the algorithm is that in each round we cut the image region that the two processors are responsible for. We cut them in half. And then, after we did this, we also doubled the distance between the pair of processors. Like I'll show this in an image in a little bit. But the idea here is basically that we perform distance doubling and vector halving. Like this is the type of algorithm that we're using here. Like we're again having an algorithm that only scales for a number of processors that is power of 2, right? And we'll again, in the end, we'll have a shared result. Like in the end, we'll have a shared result similar to the shared result that we had in the direct send case, where the result is basically distributed among all the processors. So here's the basic communication pattern for the binary swap algorithm with 4 processors. Like, as we know that we have 4 processors, we also know that we will have 2 rounds, like the height of the tree will be 2. And in the first round, we'll start with the original rendering assignment where each processor holds its own intermediate image. And we're now sending parts and compositing parts of the intermediate images. And what we first do is we will group the 4 processors into so-called communication groups. Like we will have processor P0 and processor P1 form a communication group on this round. And we'll have processor P2 and processor P3 form a communication group on this round. And both of them will now be responsible for compositing half of the image. Like, those aren't quarters anymore. Like in the direct send case, those tiles were like quarters, but instead they are now halves of the image. Like this is a half, and processor P0 is responsible for compositing half of the image, and processor P1 is responsible for compositing half of the image, but they are both not responsible for compositing this half in full. Like, they'll not fully composite this half of the image, but they'll only composite it with respect to the shares of processor P0 and processor P1. Like, when this round here has finished, we'll have 2 halves of the image that are halfway composited, right? Like, we'll have 2 half intermediate images that only contain all the fragments from processors P0 and processor P1. That is, we are not finished yet, but we also need the result from processor P2 and processor P3, and those at the same time do the very same thing. Like, the distance between the processors in the communication group here is 1. Like P1 and P0, their distance is 1, and the same is true for P2 and P3. And they are both responsible for half of the image space. So in the next round, we will double the distance. Like, now processors P0 and processors P2 form a communication group, so the distance is 2 now. And the same is true for P1 and P3, like their distance is 2. And we will now cut the image region that the 2 processors are responsible for in half. Like, now, the participants in the communication group are responsible for compositing a quarter of the image. Like, not a half, like in the first round, but only a quarter of the image. And the quarter of the image obviously contains, like this quarter of the image here already contains the result that was swapped into by processor P1. So we're now basically compositing a quarter of the image where the result from P0 and P1 is already in. And we're now adding to that the intermediate result from processors P2 and processors P3. So what we're basically doing is we're doubling the distance and we're halving the vector, like we're halving the work. And this is the whole idea behind the binary swap algorithm. Like, two remarks are in order here. Like, the first remark is that in each round we have the pairs of processors performing a direct send. Like, going back to the slide, this is kind of obvious. Here we're just in this communication group, like in the communication group that is formed by P0 and P1, we have the two processors performing a direct send over half of the image. And the same is true here. So basically we have an algorithm where we perform on each round in each communication group a direct send. Only that the number of fragments and pixels that the processors are responsible for are different than with the original direct send algorithm. And therefore, the potential contention on the network due to many messages being sent at the same time is mitigated a bit. And we of course buy that at having more rounds. So this is the first remark. And the second remark obviously is that a binary swap, like the binary tree approaches in general, will only scale on P equals 2 to the k processors. So it's limited to power of 2, and that's of course problematic. Like, for instance, like if you're like in a network that has like a general number of processors, we would probably only have like a power of 2 number of processors participate in the actual computation, and the other processors would be idle. And that's going to of course be pretty problematic. Like, if we have a network of say 63 processors, then we would only have work for 32 processors, and that of course defeats the purpose of the whole thing, right? So, and for that, I'm now going to discuss a generalization of the two algorithms, basically, of the direct send algorithm, of the binary swap algorithm. And we therefore need to introduce a bit of notation. We therefore let R be the number of rounds, like what we already saw, as the height of the tree. So R is the number of rounds, and K subscript I is the number of processors per round per each communication group. So, and with that, we can form the so-called K vector is the vector of KIs. So let me just give you an intuition by showing you what that would be just for direct send and for binary swap. Like, for direct send, R would be 1 because we have exactly 1 round. And our vector would be a vector of size 1, right? Because we have exactly 1 communication group. And the size of the communication group is P. So all the processors participate in this communication group. And for binary swap, we would have log P rounds. Like, this is just proportional to the number of tree levels that we have. And at the same time, we have per round, per communication group, we have 2 participants. So our K vector would just be a sequence of 2. So, and with this simple definition and those simple observations, we can construct an algorithm that is called the radix-k compositing algorithm. And the radix-k compositing algorithm just takes as input a number of processors P and a desired number of rounds, and then computes a factorization of those processors into rounds. That is, it will compute a K vector, and based on that K vector, we'll form communication groups. Like, here's a simple example. Like, say we have 12 processors, and I want to note here that P is not a power of 2. And the possible radix-k configurations for that would just be all possible factorizations given rounds that we choose. Like, for instance, if we decide that we want to construct an algorithm with only 1 round, then the size of the communication group on that single round would be 12, and we effectively would perform a direct send. So, and if we say want to have 2 rounds, then there are a number of certain factorizations, and those factorizations which tell us the size of the communication groups that we have on each round.
And we can do that for other integer factorizations. And inside the communication groups, we would just perform direct send. So our algorithm would factorize the number of processors into rounds, would construct a k vector based on the factorization. The k vector would tell us per round how many partners are there in the communication group. So it would tell us the size of the communication group. And inside the communication group, we would perform direct send. And you can already see this from the image here, how the data would be distributed and how the work would be distributed among the various processors. Like here in the example, we have a factorization of 12 processors into 2 rounds. We're given p equals 12, and we also decided for an algorithm with 2 rounds, and that gives us this factorization here. And in the first round, we would therefore have a communication group of size 4, and that leaves us with 3 communication groups on the first round. And you can see how the 12 processors are distributed into those 3 communication groups of size 4. And then you can see that all those communication groups internally perform a direct send. I'm illustrating this for the first communication group here, or for the communication group where processors P8, 9, 10, and 11 are in. And the other groups would work similarly on their own part of the image. And that would basically, communication group number K1 here, this upper communication group here, would basically compute for its share of the image, for the part of the image that the processors are responsible for. They would compute the third of that. The image would be composited, but actually only a third of that. And the other 2 groups would hold the other thirds of the composited image, and those thirds would then be processed in the second round. And in the second round, we would have a different assignment of processors to groups. We would now have groups of size 3, and the groups of size 3 would now composite those thirds. This group here as the third of the image, the third of the composited image that this group here was responsible for. And the second group would be responsible for a composited image that was composited to a third, where only a third of the actual fragments are already in. And with this type of factorization, we're actually quite flexible in that we can accommodate other processor counts than strictly power of 2. And this is important. It's usually a very tough restriction to guarantee that we have a power of 2 number of processors. So we already said that direct send and binary swap are valid radix-k configurations. So radix-k is a generalization of the 2 algorithms. And it is also noteworthy that the naive round-based algorithm is not a valid radix-k configuration, and that is because the naive algorithm doesn't perform a direct send inside the communication groups. And with that, I want to finish our discussion on sort-last compositing algorithms. Sort-last compositing algorithms are quite important when it comes to visualization of large 3D models and large data sets, where the data won't fit into the memory of a single compute node, and where we have to distribute the memory across a cluster of PCs or among the nodes of a supercomputer. And then we render the data in parallel, and then in the end we composite the images. And when we have many nodes that participate in the rendering process, then we need efficient sort-last compositing algorithms. So far, we have talked quite a lot about data parallel rendering in the context of large data sets and of scientific visualization that is performed on a cluster of PCs or on a supercomputer. And I want to point out that there are also other aspects of parallel rendering, and one of those aspects I'm going to devote a couple of minutes to. And this aspect of parallel rendering is so-called wavefront ray tracing. In the session about ray tracing, we already saw that it is quite easy to parallelize a ray tracer. Again, what people commonly do in order to parallelize their ray tracers is they parallelize over the outer loop over all the pixels. And that is usually fairly simple. In the simplest case, you just put a pragma OMP parallel 4 on top of the outermost loop, and then you're done. Like people usually optimize this a little bit. Like often people use tiling, like where they divide the screen into tiles of size 8 by 8 or 16 by 16 or so, and then put those tiles in a work queue and have the threads retrieve work from the work queue, and that helps a bit with load balancing. But generally, parallelizing a ray tracer in this way is fairly simple. Like, this is really not much work to parallelize a ray tracer in this way. It's actually a pretty obvious type of parallelization. But during our discussion, I already said that there are also other ways to parallelize a ray tracer. And one way to parallelize a ray tracer is so-called wavefronts. And wavefronts help a bit with a coherency of data. Like wavefront ray tracing falls into the category of sorting and compaction that I briefly mentioned when we talked about parallel algorithms. And wavefront tracing basically can be thought of like a breadth-first traversal through the ray tree. Like in particular, when you have ray trees that diverge quite a lot, then wavefront ray tracing can help quite a bit. Like in wavefront ray tracing basically sees us sorting our arrays into a list or into an array, and then have our threads like process that list. Like we have our arrays in that list, and then we have a parallel for loop running over that list, and then all the threads perform intersect on the list of arrays. So, and some of those arrays will hit something, and some of those arrays won't. And this information we can use to either shade those arrays or to mark the arrays inactive when they didn't hit anything. And that way we can, on the one hand, like perform the shade operation on those arrays that are still active, and we can do this in parallel again. And we can, on the other hand, compact the list by sorting all the inactive arrays to the right of the list and not handling that part of the list where the arrays are inactive. Like we have a sorting and compaction scheme in that we, on the one hand, compact, which is quite clear. Like the list will get shorter and shorter whenever arrays don't contribute anymore, like whenever paths end due to one reason or another. And so the list of active arrays is then shaded, and then new arrays are generated. Like we will generate new secondary arrays, like for instance here in this example. Like array 5 in this example is inactive, and the other 4 arrays they hit something. Like, and then we again have our wavefront, and we construct our wavefront, and then we call intersect on the whole wavefront again. And the wavefront potentially hits, like in this example, all the arrays from the wavefront hit something. And we can also see that the arrays like diverged quite a bit now. And as a matter of fact, like the neighbors actually hit different objects. And with this kind of scheme where we have wavefronts of arrays that are successively handled by threads in this iterative fashion, what people usually do is that they sort the arrays, and therefore it's a sorting and compaction scheme. And one very common scheme that people use is that they sort by material ID. So in this case, you would sort your arrays in a way that arrays that have to shade the same geometry, like the same material, are next to each other in memory. And then you can apply certain optimizations, and that you have like a batch of arrays being processed that has the same, that operates on the same material. And then you can perform memory optimizations, like you can make sure that the material is loaded from memory only once. So wavefront ray tracing mostly is a memory coherency optimization, in that it allows us to sort the data in between, which is actually pretty helpful. Like when we can sort the data in between, that can actually help quite a lot with coherency. Like on the one hand, when we sort by material ID, it's highly likely that the rays that will next be reflected also hit the same geometry. Like when we try to group together rays that intersect the same geometry, then like in all likelihood, they are also close by. And there are actually other ways to sort our wavefront. Like some people, for instance, sort them by their origin, like in that they project the ray origins on a grid and then project the direction vectors to octants or so, and then sort them by that too. So there are also spatial sorting schemes. But the idea is basically that you have this breadth-first traversal through the ray tree. That is, you have parallelism, where you have basically a barrier after each intersect step and after each shade step. And the barrier obviously comes with a bunch of overhead, like because you have more synchronization than you had before. But that gives us the opportunity to sort the workload for coherency in between. Yeah, and here's just another schematic of this principle. And wavefront ray tracing is helpful when the workloads are very divergent. Like in particular because of the compaction phase, because the compaction phase helps us to figure out when threads don't have any work to do. Like in the simple way to parallelize a ray tracer over the pixels, it can happen that we have threads that don't have any work to do and other threads, like they are processing like a handful of pixels that are still active and performing bounces. And due to the compaction scheme, this is less likely because in the end, like when we have those 5 pixels left, then we can also make sure that we still devote all the parallelism that we have to those like 5 pixels, or like maybe 5 tiles, depending on what the granularity of our parallelization actually is. So wavefront ray tracers are usually used when the workloads are quite divergent, like in a path tracer where we know that we perform many bounces. And wavefront ray tracing, of course, has a lot of overhead. Like we have to, per bounce, stop the whole pipeline. And of course, that causes a lot of synchronization overhead. Sorting, of course, is optional, but can actually help a bit. But this actually depends on how complicated your materials are. Like when you have very simple material, then your mileage may actually vary pretty much. And it's really undecided, in my opinion, if sorting helps that much or not in this very case. Like if the materials are very complicated, like for instance, if you have certain materials that have a procedural texture and other like have like a bunch of textures because they're like physically based materials, then wavefronts actually have helped quite a bit because like when you have very complicated materials, those are likely to thrash both the instruction as well as the data cache. And then it should be said that on certain architectures, and in particular on GPU architectures, wavefronts don't work well. Like for instance on the RT-Core architecture, it's pretty important that we let the GPU schedule the rays themselves for highest throughput in regard to how we use the ray tracing hardware. Like we're currently like discussing alternative types of parallelization for rendering, and yet another alternative type of parallelization for rendering is so-called distributed shared memory. Like this is again yet another completely different type of parallelism that we're discussing now that has nothing to do with the wavefront ray tracing that we discussed before, or with the sort last rendering. And like distributed shared memory, however, is a scheme that makes things actually much simpler when it comes to parallel rendering. Like distributed shared memory systems basically emulate a shared memory system on top of a distributed memory system. Like think of like we have a cluster of PCs, and then on top of that we have a layer that makes the software that we're like the software renderer that we're running on top think that it is running on a shared memory system. And like under the hood, the distributed shared memory layer might implement something that is actually quite similar to the cache coherency protocols that we discussed when we talked about parallelization and about NUMA architectures. And like under the hood, those systems often use like message passing and very similar ideas to what those cache coherent NUMA systems actually did. And this is, for instance, quite useful when you perform sort first rendering. And when you want to make it appear to your rendering system that the data is shared, like, and then the DSM system under the hood, like the distributed shared memory system under the hood, will distribute the geometry whenever this is necessary. And to the actual processors, it appears as if the geometry is shared. So we now discussed quite a lot of types of parallelization. Like there were different aspects of parallelization that were relevant in certain situations. Like the Molnar taxonomy, for instance, is relevant in all sorts of situations, and we already saw that it was like at least originally targeted towards rasterization and GPU architectures. And our discussion at least should illustrate that there is a lot of parallelism in graphics. Like the typical rendering systems, they make quite a lot of use of parallelism. And this is important to note, and this is also important to note in order to understand how GPUs work. So GPUs are quite parallel systems, and this is there's a reason for this. And like when we are talking about GPU architecture, and we'll start our discussion about this very soon, then all these considerations about parallelism become like pretty important to us. And therefore a solid understanding of what type of parallelism there is in a typical rendering system or a typical rendering algorithm is pretty important. And with that, we will close our discussion on rendering algorithms and computer graphics. And let us therefore quickly reflect what we have learned so far. Like, we have learned about computer graphics basics, like about the light transfer equation and about scan conversion, texturing, depth buffering, etc. And we learned that those are basically just building blocks to other more advanced algorithms, like for instance the rasterization algorithm that forms the basis for what we today call the graphics pipeline, and what we'll talk about in depth very soon. And the graphics pipeline, or the rasterization algorithm, consists of a couple of stages, and we learned how to formulate this algorithm in a way that we can achieve maximum throughput on each of those stages. And then we learned about deferred shading as a extension to the rasterization algorithm, which basically defers the lighting stage, and with that is able to improve the asymptotic runtime of the algorithm like a little bit, but at the cost of extra storage overhead, and at the cost in particular of having to access buffers with higher bandwidth demands than we have to do this with the rasterization algorithm. And then we also talked like a lot about ray tracing. Like ray tracing is actually an algorithm that lends itself pretty well to an implementation on GPUs. And ray tracing is also relevant because ray tracing is nowadays supported by NVIDIA, at least in hardware. Like NVIDIA has this RT-Core hardware which basically accelerates ray BVH intersections. Ray tracing is a highly flexible algorithm. Like, you generally, in order to obtain more realism, you just basically throw more rays at the problem. And due to that, we require acceleration data structures, and those acceleration data structures can reduce the complexity. Like when we would naively perform ray primitive intersection tests, we would just intersect the rays against all the primitives in a linear fashion, like a linear search. And this is customarily optimized using acceleration data structures to get the asymptotic complexity down to a logarithmic complexity. So, and then the last sessions, we also learned about parallel rendering, and ultimately the discussion of parallel rendering will help us to better understand what's going on GPUs, and how parallelism is exposed, and how parallelism is put to use on GPUs nowadays. So finally, I want to recommend a bit of literature, like the book by Peter Shirley, Fundamentals of Computer Graphics. It's really an introduction to basic topics of computer graphics. So there are actually a bunch of other books by Peter Shirley that you might check out. Like for instance, there's this series called Ray Tracing in a Weekend, and the book is for free, and you can download it from the internet. And that's actually pretty helpful to get a better grasp of ray tracing. And like the ultimate literature when it comes to ray tracing is Farr and Humphrey's physically based rendering. And the book is by now available in its third edition. Like the authors present a CPU ray tracer, and the CPU ray tracer has like many features, like lots of features that are very relevant to production. And the authors are currently working on a fourth edition, and the fourth edition will actually run on a GPU. Like, it's a huge novelty in regards to the former design of the ray tracer. And it's like really one of the best books about ray tracing in order to understand ray tracing. Like, the book actually won an Academy Award some years ago for its contribution to the movie industry. As a matter of fact, very recently, like this year in 21, researchers from Saarbrücken won an Academy Award. Like, they are the developers of the Intel Embry library, the Intel Embry ray tracing library, and also won an Academy Award for their achievements for the movie industry. And this illustrates pretty well in which industry ray tracing is important nowadays. So for our discussion on parallel rendering, I can recommend the High Performance Visualization book, which is more like a compilation where several authors contributed to. And it discusses a bunch of topics that we also discuss that are relevant to visualization at scale, like when you have large data sets and when you have many processors. Yeah, and then like there's a bunch of papers that I also mentioned in line, and most notably there's the paper by Pineda that you should have a look at. Like the Pineda algorithm in general is pretty relevant for us, and so is also the ray tracing algorithm. And one of the most important papers, or like one of the earliest papers there actually, is the one by Trainer-Whitted, which describes the Whitted ray tracing. Well, like there's a whole corpus of papers and of literature on both ray tracing, but also on other computer graphics topics. And this is really just a tiny sample of the papers that could and probably should be mentioned in a list like this. And with all this knowledge about computer graphics and rendering algorithms, we can now finally go over to what I call the architecture part of this lecture. And the part is titled The Graphics Pipeline. And we will learn about just that. Like we will discuss the graphics pipeline. And the graphics pipeline actually begins at the so-called interactive host interface. That is where the application issues commands. And the commands are then processed by what is called the command processor, which is the entity on the GPU that takes those commands and then routes the commands through the GPU architecture. And we will discuss the GPU architecture and we'll understand how it relates to the rasterization algorithm that we discussed in the previous sessions. And we'll also learn how this architecture maps to modern graphics APIs, such as, for instance, Vulkan or DirectX 12. So when I want to start this part of the lecture with a discussion on what I would call traditional or legacy graphics APIs. The idea is that we understand how graphics APIs worked traditionally, and then we will gradually understand how a modern GPU architecture, in contrast to that, would work, and we will try to understand what the potential shortcomings of those APIs are, and this will prepare us for a later understanding of how modern graphics APIs like Vulkan or Apple's Metal or Microsoft's DirectX 12 have evolved into what they are today and how they map to a modern GPU architecture. And the very first thing that we should discuss is graphics API behavior. Like what I'm going to outline in the following is not necessarily a data model. So the in-memory representation of the graphics API doesn't necessarily look like what I'm presenting you now, but it is mostly a behavioral model. That is, this is how the graphics application developer perceives the API and how it is used. Like there are two fundamentally different modes how a API can behave, and the one mode is the so-called immediate mode. And in the immediate mode, we assume that we have our graphics API, and the graphics API talks like to what I kind of generally call the display here, which is usually much more complicated, but the behavior is that there is a graphics API, and our application can talk to the graphics API, and that will result in like an image being displayed. And in the immediate mode model, the application is assumed to hold all the data of the three-dimensional scene. And when the user interacts with the application, this results in the application modifying the three-dimensional scene and then translating that into draw commands or into copy commands that tell the graphics API to copy data to the GPU. And like in general, we have a model where the application maintains the internal, like three-dimensional state of the scene and also applies updates to the scene. And then the application translates that into graphics commands, which are like usually like draw commands or like different commands that the graphics API understand. And the graphics API takes those commands and translates them a bit and then basically routes them through to the display that can process those commands and turn the commands into an image. And this is what we will call immediate mode. And that basically sees whenever we have the user interacting with the application, sees the application maintaining updates itself and then issuing draw commands, and the graphics API understands those draw commands and routes them through to the GPU or to whatever instance there is that displays the image. And then there's the so-called retained mode APIs, and those retained mode APIs basically have the graphics API logically store the three-dimensional scene. And the application can take user interaction and can interpret user interaction and translates that into update commands. And those update commands is what's understood by the graphics API. So the graphics API doesn't think in like understanding and then translating draw commands, but it thinks in taking update commands and applying those to the scene. And the graphics API will then internally translate those updates or those changes to the three-dimensional scene and to transformations that influence the behavior of the scene, or like how we view the scene, and like camera parameters, etc., and will translate that into draw commands and will issue those draw commands to the GPU so that the GPU can finally display an image. So those are like two fundamentally different types of graphics API models, and it's important to understand the difference between those two models, and we'll in the following concentrate on immediate mode APIs. So we have those two APIs, like on the one hand the API that only understands draw commands like draw a triangle and draw another triangle and draw another triangle, and then in the end they like form a sphere or a house or whatever, but the library doesn't understand that, but only understands that there are draw commands. And on the other hand, we have this graphics API that understands the scene and maybe also the hierarchy that is underlying the scene, and understands the scene as an entity or as a set of entities, and also understands update commands to those entities and translates that into draw commands. And the typical traditional 3D APIs were, like OpenGL for instance, were immediate. And we have an API where the application developer issues draw calls, and the API behaves as if those draw calls are like directly executed, like they are executed immediately. While with the other API, we're issuing like 3D entities and we're issuing updates to those 3D entities, but the actual draw calls are retained. And like in reality, this is like the exact opposite, like the immediate mode APIs are the exact opposite of how a GPU behaves. Like the GPU is bounded by certain bottlenecks. Like for instance, by a very severe bottleneck in that when we copy data over PCI Express, there's really high latency. So if we really had an API that would really immediately draw a triangle as soon as the application developer issues a draw command for a single triangle, then this API would starve itself to death. Because we would like for every triangle have a communication over PCI Express and would have an extraordinarily high latency only for drawing like a single triangle. So the actual GPU model underlying the graphics API is like fundamentally different, because typically with such a model we would have, on the other hand, a very complicated driver, and that driver would obtain the draw commands from the graphics API. So the graphics API and the driver would like work hand in hand, and the driver would, before it would actually send the draw command to the GPU, would first buffer them. And then the driver would implement some types of heuristics, like heuristics that tell the driver when to actually send draw commands to the GPU. And when we think of how systems looked like some 20 or 25 years ago, those systems, like for instance graphics workstations, They were often like even single user systems, and quite often like there was only ever one single process that would actually issue draw commands to the GPU. And in a scenario like this, a driver that buffers draw commands and then sends draw commands to the GPU in batches might be relatively simple to implement. But now consider a driver that has to do the same thing, but in the presence of multi-user, multi-process operating systems, where different processes like concurrently can issue draw commands from multiple processes, and in some cases even from multiple threads in a single application. And the driver has to like batch those commands and make sure that they are synchronized appropriately and that the data dependencies are still resolved when the draw commands are issued to the GPU. And you can imagine that in the presence of modern days operating systems and in the presence of modern day programming models, such a driver can become quite complicated and has to incorporate quite complicated heuristics. And this was like a problem with traditional graphics APIs. Like the traditional graphics APIs, they concentrated on the actual process of drawing, but they didn't reflect in any way how the underlying hardware worked, and in particular not how like modern GPUs work. So we'll discuss this discrepancy in the following, like this discrepancy of immediate mode graphics APIs on the one hand and of GPU architecture on the other hand, and we'll do that by considering OpenGL. And the code that I'm presenting is not necessarily valid OpenGL, so I never compiled and tested the code. And in certain situations, I also know that some calls are like oversimplified and that the interfaces of some calls are a bit simplified. So currently it's mostly about the understanding, like about understanding those immediate mode APIs and what the implications of those APIs are, and what makes those APIs difficult to implement on modern architectures. And when we have an understanding of that, we will also understand how modern graphics APIs evolved, which make certain things completely different than the traditional immediate mode APIs. So in the very early days, immediate mode APIs would behave something like this. Like we would tell the APIs that we're drawing a certain primitive type, like for instance triangles, and the API would usually like understand some types of polygons, like triangles, quads, strips of triangles, general polygons, and so forth, and we would tell it which type of primitive we would like to render. And then we would, like one vertex after another, specify our triangles. Like we would do this for each and every triangle, like loop over like a list of triangles and specify all the vertices. And then whenever we like want to draw a different color, we would specify that too. And each of those calls would be like at least a call into the API, and the API would do, well, whatever it does with the vertex that we pass the API, but the behavior of the API would be completely immediate. Like we would expect that the order of execution is the very same, like when the API issues actual commands to the GPU, that it adheres to the order in which we are issuing the API calls. And we would also like expect that those calls would like manifest immediately. At least this is the behavior of the API. And like under the hood, we already discussed that there's something different that happens. Like under the hood, we at least nowadays have hardware that is massively parallel, and that is optimized for throughput, and that is it requires that data is sent in batches. So a typical GPU nowadays has a data path that on the one hand exposes very high bandwidth, like in comparison to other processor models, and on the other hand exposes very high latency. That is, whenever we require that bandwidth, we pay that at the cost of very high latency. So it is clear that at some point we need to buffer, and we on the one hand need to buffer commands, and we also need to buffer data. And the question now becomes who actually does that? Like when the driver does all the buffering, that's actually good for developers' productivity, because the developer doesn't really have to care when data is actually passed to the GPU and when the GPU gets involved. And on the other hand, the developer might have some application-specific knowledge. And that would give the application developer more potential to optimize for the GPU architecture that is used for rendering. And therefore, there's some potential to see an increase in performance when using an API where the application developer is responsible for buffering. So with the very old APIs, we had those immediate modes where even the data was specified like on a granularity that we specified each and every vertex in a separate call, and graphics APIs evolved from that pretty soon, in that they became hybrid, in that at least the data could be buffered manually. So the API still stayed, and even until today stays immediate. Like the OpenGL API is still in immediate mode API, but with a bit more recent versions, things changed in that at least the data could be buffered by the application developer. So the application developer would create a buffer and bind a buffer, and would then fill the buffer with data, and would later then bind the buffer again for drawing. Like the application developer still doesn't really control when the actual copy happens. Like this is not a memcopy command, but it's really only a command that binds a buffer and that tells where the data for that buffer comes from. But we don't control things like when actual copies happen and what the actual memory region is that is being used for the buffer. But at least the application developer had a bit more control about how to bundle and how to batch the actual data that is sent to the GPU. So with data, it became quite clear at some point that the application developer needed some sort of control over how data is buffered. But in general, the immediate mode APIs, and in particular OpenGL, have a state machine, and this state machine will execute the rasterization algorithm, and it will allow for configuration, and it will allow for configuration through commands that instruct the GPU to set up a certain state before draw commands are issued. Like the typical control flow of a OpenGL application would look something like where we configure OpenGL to set up certain state. So we would, for instance, tell OpenGL that the current state has an active texture that is bound to the texture unit 0, and would then bind an actual texture to that texture unit, would fill the texture with some data, would enable certain lighting conditions, would set a camera matrix. So all that would set up the state of OpenGL, and the currently bound state would then be used when the application developer specifies draw commands. Like the application developer specifies application calls, and those application calls set up a state, and the state changes are immediate, and the state applies to the next draw calls. And as a matter of fact, the state changing API calls will later also manifest as GPU commands. So in the immediate mode APIs, we traditionally had a state that was configured by the application developer, and that the GPU adheres to when a draw call is issued. So when the draw call is issued, the GPU will consult the state and will try to find out how to actually draw the data that the application developer specified. And there were certain API calls, or there are still certain API calls, as this is still the way that you program with OpenGL, and those allow you to modify the OpenGL state. And when a certain state is active, and with a certain setup for the state, when the application developer issues a draw command, this state is used to actually perform rasterization. And in order to maintain the state, OpenGL uses something that is called the context. And the context can be thought of as a huge object that contains all the state, and that contains all the state in regards to a certain application with a window that we draw into. And the context is also usually associated with threads. Like OpenGL per se doesn't think in threads, and there's usually a operating system layer on top that performs thread management. And originally, OpenGL was never designed with threads in mind. So we have those states, and they are like quite heavyweight objects, and the state determines how we render, and the state manifests as an object that is called the OpenGL context. And so if we were to like execute in an OpenGL application, this would look like something like as follows. Like we would create a window, and then we would use OpenGL in our application. And when we would issue the first OpenGL calls and would have OpenGL interoperate with the windowing system, then OpenGL would create a context like under the hood and bind this context to the current thread. So then our application would like initialize a frame buffer, would initialize a back buffer, etc. And this would modify the context so that the context knows where to render into. And then in our OpenGL application, we would start something that is called the render loop. Like we would usually have some user interaction, and that user interaction would influence like the camera or maybe how objects are arranged in the scene. And the render loop would be able to process user interactions and user messages and would translate that into changes to the scene, to the geometry, and also into draw calls that are issued to OpenGL. Whenever doing so, the application issues draw calls or changes the current camera transformation, for which OpenGL actually had something that is called the matrix stack, which allowed us to hierarchically modify the camera transformation. We will talk in a bit more detail about this later, actually. And suffice it to say that the matrix stack was also part of the state. Like the whole state, which manifested as the context object, was a relatively complicated and heavyweight object. Like this is the basic control flow. Like we have our context and we have our state. Like for instance, we tell OpenGL that we have a diffuse material and that we have a specular color of white and some certain light configuration. And then we would specify the geometry buffers that we're rendering. We would render another geometry buffer, and we would send up a new state. And the state would, for instance, be comprised of some semi-transparent geometry, so we enable blending. We might actually set some clip planes, and all that influences the shading state, like the OpenGL context. And then we would at some time present the geometry by issuing a certain command that tells OpenGL that we're now actually finished modifying the state. So an OpenGL would internally store that in the context, and the context is something that's like implicit. Like we will never be able to like explicitly access a context object from within OpenGL. But suffice it to say that it is like a huge object. Like think of it as a huge class or C struct that stores all the state. And as you can imagine, a very heavyweight state object can be quite inflexible. Like when we are thinking an API, like we're thinking an API that is designed for a single user, single application, single process execution, then this type of execution mode might make sense. Like we would have our state somewhere, and the application would modify the state, and the state would be like stored in some global region, and the draw commands could have like access to that state and would know where the state is. But things become much more complicated when we have like multiple applications maintaining different states at once. Like that way, we would not have only one context, like one global context that can be stored on the GPU somewhere in some dedicated region, but we have a variable number of contexts that were potentially active at the same time. So the GPU would have to disambiguate that and would have to figure out which draw call belongs to which thread and which thread currently maintains which context, and then would have to figure out how the current draw calls and the GPU context that it maintains, how they match. And this is obviously in contrast to how GPUs work nowadays. And in the next session, we'll look more into OpenGL and we understand more about OpenGL, and we also look more into the discrepancy between current GPU architectures and between the traditional immediate mode APIs. We'll also learn a bit about how GPUs and drivers handle that on the host interface side. Like there are certain ways how GPUs can actually cope, and we will learn a bit about that. And by that, we will also understand how the handshake between graphics API and graphics driver on the CPU side and the command processor on the device side work. And those entities together form what is called the interactive host interface. And the interactive host interface will be one of the topics that we will discuss in our next session.